If you look at the molecules they give you in exercise 2116, you'll notice some similarities. You have a carbonyl with 1, 2, 3, 4, 5 carbons in both molecules. A carbonyl with 1, 2, 3, 4, 5 carbons. The difference is one is a straight chain and the other is a ring. In one, you have the carbonyl, carbon, bonded to an OH. So you have a carboxylic acid. And you want to think of that other group on the carbonyl as a leaving group. You have that, and on the other end of the molecule you have an OH, which can function as a nucleophile. In the product, the OH is gone, and it's been replaced by an ester, the carbonyl bonded to an ether. So, in other words, we've taken a carboxylic acid, we've reacted it with an alcohol, and we've gotten an ester. Now you'll recognize this as the Fischer esterification. We've drawn a mechanism like this already in a previous video. But it's a really significant reaction, and I think it's worth taking the time to draw the mechanism again in this case, because first because it's so significant, but second because in this case it's an intramolecular reaction, something that's sometimes hard to visualize at first, but really only requires the same conceptual machinery that we've built up so far. It's the same alcohol reacting with the carboxylic acid to give you an ester. It just so happens to be a cyclic ester. These cyclic esters, by the way, are called lactones. The ONE is sort of referring to this, what almost looks like a ketone, but they're called lactones. Now, obviously, it's not a ketone, it's an ester, but here we go, lactones. So let's draw the intramolecular Fischer esterification of this molecule. Okay. Well, the first thing we'll notice is that we are going to have to do a lot of proton transfers. The carbonyl carbon is slightly positive, but it's stabilized a little bit by the lone pairs, which are allylic to the pi bond and therefore move closer to the pi bond in another resonance structure and help stabilize the positive charge on that carbon. So it's not the best electrophile. It's a decent electrophile for sure, but not the best one. And because of that, we need an acid catalyst, and you notice that that's written above the reaction arrow there. So we have hydronium. The purpose of the hydronium is to turn our mediocre, if not slightly bad, electrophile into an awesome electrophile. And we need that because our nucleophile does not have a full charge on it, so it's not itching to react. It's perfectly fine being the way it is. So if we want to lure it into reacting, then we have to make the electrophile really tempting. So we can make this more reactive, we can make this a better electrophile that's more likely to react by doing a proton transfer. And that should make sense. We've seen this pattern. Proton transfers change the reactivity or stability of molecules. We want this to be more reactive, so we can do a proton transfer. The slightly negative oxygen in the carbonyl can attack one of the slightly positive hydrogens in the acid. The electrons would snap back onto the oxygen there to stabilize the positive charge. So after that proton transfer, we have water. Hydronium will have turned into water. And then we'll have this same molecule, but the oxygen, instead of having a lone pair, will have a bond to a hydrogen. Because that oxygen is bonded to 3 things, it has a full positive charge. And it uses the power of that positive charge to really pull electrons to itself. And when all the electrons on the carbonyl carbon sort of go to that oxygen, the carbonyl carbon becomes really slightly positive, and so now it's a much better electrophile. It's a much bigger charge than existed above. Okay. Well, once we have that, our nucleophile, our alcohol, oxygen, which is slightly negative, can attack. So this can wrap around, attack the carbonyl carbon, the pi bond will break, and the electrons will go on to the most electronegative place nearby, which is the carbonyl oxygen. And if you're trying to classify that in terms of the 4 curved arrow patterns, that would be nucleophilic attack, one of the essential steps in any substitution reaction. And it's unique because it's intramolecular. Now, Trying to draw the product of these things when rings break or form can sometimes be tricky. My recommendation to you is to number stuff. Now, when you number stuff, when you're breaking or forming rings, you're not numbering it to name it. So you don't have to worry about where the numbers should start or whatever. You're just numbering it to keep track of things. So we know this oxygen is going to be in the ring, and then each of these carbons will be in the ring, and finally the carbonyl carbon will be in the ring. So we're going to have a 6-membered ring with an oxygen in it. So a 6-membered ring looks like a hexagon, and it will have an oxygen inserted in it. So if I'm going to number this the same way I numbered the chain above, the oxygen is number 1, and then we can go around and have 2, 3, 4, 5, and 6. Now again, you might say, wait, you're numbering an oxygen? You never number oxygens, you only number carbons. That's true, that's only when you're naming stuff, though. I'm not trying to name this molecule, I'm just trying to keep track of stuff as I go from a straight chain to a ring. And so that's why I can put a number on that oxygen, which is one of the atoms in the ring. Now I'll notice that that oxygen still has a hydrogen on it, so I'm going to draw a bond to the hydrogen, and that oxygen has 3 bonds, and therefore has a full positive charge, and a lone pair. 1 lone pair left. The other thing we should have is on carbon number 6, we should have first, what was the carbonyl will just be an OH now. And we still have another OH on carbon 6. So this is what is that tetrahedral intermediate you would get when this intramolecular nucleophilic attack happens. Okay, well, our nucleophile is this oxygen. We want to stabilize that, so we can take the water that we had over here and use that as a base. Remember that to change the reactivity or stability of molecules, you do proton transfers. And so this is too reactive. We want that to be more stable, so we're going to do a proton transfer to help stabilize that. Now sometimes it comes undone before that acts as a leaving group before the reaction proceeds. This exists at an equilibrium, so it's constantly being formed and breaking apart. But sometimes before it breaks apart, a slightly negative oxygen on a water in the solution will steal the slightly positive hydrogen. The electrons will snap onto that oxygen to stabilize it, and we'll get a stable tetrahedral intermediate. So that stable tetrahedral intermediate will look like this. Okay, in addition to that, we will have hydronium. Water would have accepted the H+, and so become hydronium. Here. All right, well, we don't want to forget, we have our nucleophile done, taken care of. It's firmly established on the molecule, but our leaving group has not yet left. Now, right now, it's a bad leaving group. OH is a bad leaving group because if it leaves, it takes electrons with it, has a full negative charge. Oxygen is not a very big atom, so it can't dilute or stabilize that negative charge by spreading it out into space. OH- is very reactive. It's a strong base and a strong nucleophile, and so it would just snap right back onto the molecule. It's a bad leaving group. To make it a better leaving group, to make this thing that is not likely to react more likely to react, we do a proton transfer. Use proton transfers to change the reactivity or stability of things. That OH is not a good enough leaving group. It's not likely enough to react. We can make it more reactive, more likely to leave as a leaving group by doing a proton transfer. So we can take this hydronium that we made, and the slightly negative oxygen here can attack one of those slightly positive hydrogens, and the electrons snap back onto the oxygen on the hydronium. So after that proton transfer step, we will have this lone pair becoming a bond to a hydrogen, and that oxygen has 3 bonds and therefore a full positive charge. In addition to that, what was hydronium that loses an H+ and becomes water again. Okay. Well, we turned a bad leaving group into a good leaving group, an awesome leaving group. That oxygen now can take electrons with it, and it'll just stabilize the positive charge. It'll be water after it leaves the molecule, which is very stable. So we can finally do our loss of a leaving group. All it needs is a small push. And you'll notice that this carbon here, what was the carbonyl carbon, is really slightly positive. It's bonded to oxygens on 3 sides. All of them are stealing electron density from it, so it's really slightly positive and therefore very attractive to these lone pairs on these oxygens. One of the lone pairs snaps down, tries to form a bond to the positive charge, and because there's a good leaving group, it just pushes the leaving group off. And so we get loss of a leaving group. And so now we have, the same ring as before, but this oxygen has a double bond and a full positive charge, and water has left. Okay. Well, in this case, we're almost done. We've almost formed the ester, the cyclic ester, which is also known as a lactone. We just need to stabilize this positive charge. That charge is unstable. We can change the stability of things by doing a proton transfer. And so the water molecule we made, I'm just going to redraw it over here. This water molecule we made that I've redrawn, that can act as a base. The oxygen's slightly negative. It can steal the slightly positive hydrogen here. The electrons would snap back onto the carbonyl oxygen, and we'd end up with our ester. Or, technically, because it's a cyclic ester, our lactone. And that's it for this molecule. That's the molecule that they wanted us to explain the making of. That is what we had over here, that lactone. And you'll notice the water that we made is also there. So if you zoom out and think about this on a grand scale, we just saw what it looked like on a minute granular scale. But if we want to see what it looks like on a grand scale, you can see all of these steps. The 2 essential steps for substitution reactions are there: nucleophilic attack and loss of a leaving group. Everything else is a proton transfer that either made something more reactive or less reactive, less stable or more stable. Our nucleophile was not very strong, and our electrophile was not very strong either, so we had to make that electrophile more reactive by doing a proton transfer in that first step. Then the nucleophile attacked, and we had to stabilize the nucleophile with another proton transfer. It had a positive charge after it attacked. We had a leaving group that we wanted to leave, but it was a bad leaving group, so we did a proton transfer to turn it into a good leaving group, make it more reactive. Once we had a good leaving group, we did loss of a leaving group, and then we just stabilized the product that we made. It had a positive charge, so we stabilized it by doing another proton transfer. And that left us with the lactone. So this is one of the longer types of mechanisms for doing a nucleophilic acyl substitution, but very common. Almost definitely one like this will be on a test. I mean, one where you have the nucleophilic attack and loss of a leaving group sort of sandwiched in between proton transfers. And we were able to turn a carboxylic acid and an alcohol, combine those, and get an ester. That's Fischer esterification. The ester was a cyclic ester, and so we made a lactone.